Hello and welcome back to episode Pi. This is the 6th video of my series on polynomials, and today is the first episode of a two-part series on the understanding of the cubic formula. So first we've got to write down the general cubic, which is ax cubed plus bx squared plus cx plus d equals 0. First step, as always, is to divide through by a. This will get the x cubed coefficient equal to 1. And, of course, 0 divided by a will just remain as 0. And what this will look like is one of these curves, where the gradient at the middle is positive here, equal to 0 here, or negative here. And then what we actually call these middle points is we call them inflection points. And what that means is when the rate of change of the curve changes from positive to negative, or when the second derivative is equal to 0. A way to explain this is to look at these three graphs. So you have f of x on the left, which has two turning points represented by the two roots of f dash of x, the second derivative, and one in green inflection point represented by the root of the linear function f double dash of x. Next, if we were able to move the inflection point to the y-axis, it would make things a lot more simple for us to solve. And this kind of cubic would be of the form x cubed plus px plus q, which is what we are always trying to get to with cubics. To show that this is the case, that the inflection point does lie on the y-axis when we have a cubic of this form, I am going to let f of x equal x cubed plus, that's a horrible 3, I apologise, x cubed equal x cubed plus px plus q. And I'm going to find the derivative, which is f of x equal to 3x squared plus p. And then what we're going to do is we have f double dash of x equal to 6x. And when that is equal to 0 is the x-coordinate of the inflection point. And the only time when 6x is equal to 0 is when x is equal to 0 as well. And this means that q, which is the y-intercept, because when x is 0, all we are left with is q. If q is the y-intercept, and then the intersection point is also the y-intercept, then we say that q is the inflection point. So, what we need to do now is shift our original function onto our original function's inflection point onto the y-axis, as we've got up here in our example here. So, the way we do this is we write down our full function, which is x cubed plus b over ax squared plus c over ax plus d over a, and then we say that's f of x. Then we find f dash of x, which is equal to 3x squared plus 2b over ax plus ... Because I'm saying ... because they won't continue to the next phase, so they're fairly irrelevant to write at this point. Then we have f double dash of x, or the x coordinate of the inflection point when f double dash of x is equal to 0 will be equal to 6x plus 2b over a. Now, obviously, we want that to be equal to 0 because we want to find the inflection point. So we say that 6x is equal to minus 2b over a, and then x is equal to minus 2b over 6a. And what we can do now, if I'm just allowed to change the colour of my pen, so I'm just having a technical issue here. That's a bit unfortunate. There we go. So here I'm going to use red to show that I'm cancelling these and just leaving a 3 here. And that will equal negative b over 3a. Let me know in the comments if the colours help. Now, some of you will have noticed that we have a 3 here, and in the quadratics we had a 2 at this point. And you would be right in assuming that it is a 4 for quartics. I'm not going to show you in the quartic video how to do that because I want to spend more time on the cubics, and that's all I have time for at the current state of things. So what we're going to do is perform the shift. So we have x minus b over 3a cubed plus b over a x minus b over 3a squared plus c over a times x minus b over 3a plus d over a is equal to 0. What we're going to do then is we're going to multiply out the brackets. I am going to deal with each one of these terms on separate lines, otherwise it just won't fit in. So, first of all, we have x cubed minus 3x squared b over 3a. These two here will cancel. Plus 3x b, I'm sorry, I changed the colour, didn't I? I'm sorry. B squared over 9, that was pretty atrocious, 9a squared, these can cancel and leaving a 3 here, minus b cubed over 27a cubed. Next line, we have plus b, before I write that, I'm going to change colour, x squared over a minus 2x b squared over 3a squared plus b cubed over 9a cubed. And then the next line we have plus cx over a minus cb over 3a squared, and the next line we just have plus d over a, and of course that all is equal to 0. So what we're going to do next is we're now going to collect like terms, and the first thing I'd like you to note is that here we have our first x squared term, and our second x squared term is over here. These two x squared terms are equal in magnitude, so their modulus value is the same. Modulus just means absolute value. And they have opposite signs, so here and here. This means that we can just take them completely out of the equation. And that's where the x squared term is lost, as we have our x cubed plus px plus q. Now we're going to factorise this a little, and this will give us what we are originally aiming for of x cubed plus c over a minus b squared over 3a squared x plus 2b cubed. Now another one. Will Peter fit it in? 2b cubed over 27a cubed minus cb over 3a squared plus d over a. I did fit it in, and that of course is all equal to 0. Okay, I didn't fit the 0 in. And as you can see, this is of the form x cubed plus p of x plus q equals 0, where p is equal to here, this term, and q is equal to this term. So that's the derivation of this format at the bottom. And in the next video, we will look at the derivation of the discriminant. Anyway, thank you for attending episode Pi, and I look forward to seeing you in the next episode.